Okay, let's get started. All right. So two things. I have an escort today, my 20-year-old daughter in the back. She's the artist in the family. If you ever wondered why I have an anime here on my computer, that's because she is an animation major in AMCAD. So no science background. She said, walking here, you guys are not cool. At AMCAD, we're cool. Like, okay then. All right, the second thing, I won't be moving around a lot. I am lightheaded, so I'll be sitting here. But I'll be as enthusiastic as ever teaching you guys, but I'll be not very active. Okay. So I have to write down the groups that got +2. Hey. All right, are you guys ready? No? Hey, made it again. B stepped up. Cool. And E made it again. All right. So let's go back to finishing up chromatography. I know Gary finished up mass spec with you. I'm a little behind. I should have started spectroscopy by now, but we'll finish chromatography, and I still have the HPLC lecture, which is going to be a refresher for you because you already did the HPLC lab. So let's remember where we were. What is peak resolution? Isaac in the back.
That when you clearly define one peak.
Yes. So it's the separation of the peaks that you're interested in. What is a solvent front peak? Ash?
It's the very large peak that you get at the start of your manogram. That is where most of your solvent comes in.
Yes, so it's the solvent peak, and basically it doesn't have to be large. It's large in GC and it's very small in HPLC. It represents the void volume of your column. So basically the time from injection to the solvent reaching the detector, the solvent gonna say, okay, I'm here, the detector is gonna identify it and gives you a peak. In GC, it's really large. In HPLC, it's a tiny peak. What's the difference between retention volume and retention time? All right, Lisa?
Retention time is the time between the injection of the sample and the removal of the sample. And then the volume would be the retention volume is the volume of the sample that leaves the column.
Yeah, so it's the volume. Actually, you're right with the retention time. So retention time is the time it takes from injection to the elute or the compound or the solute to get out of the column, and you see a peak for it. Whereas the retention volume is the volume of the mobile phase that took to get that solute out. And usually we really care about retention time. It's very rare that we care about retention volume. What's the relationship of peak width to resolution? So meaning as the peak width increases, does that mean resolution goes down or the other way around? Tim?
It's the inverse or relationship, meaning that the wider the peak is, the worse the resolution is.
Absolutely. So when you have a wider peak, that means it took a long time to reach equilibrium between the stationary phase and the mobile phase. And there's more probably longitudinal diffusion rather than going in and out. So the solute band widens and then it gives you a wider peak. And when you have wider peaks, if you have two peaks close to each other, you might get coelution. So that's something you don't want to happen. What is the first step in developing a separation between solutes of interest in your sample? So the first thing you do to start chromatographic separation, what is it? Yes, Carol.
You're gonna like to see what other people have done.
Yes, yes. Wasn't that Kevin who answered that question last time? Yeah. All right, so first thing you do is look up what other people have done. Sometimes it doesn't work for you, but it's a good start. All right, so let's continue where we left off. We finished talking about the efficiency of the column and the number of theoretical plates. Now I'm going to talk a little bit about selectivity. So first of all, when you remember when I first started talking about chromatography, the first important thing that needs to happen is for the solute to interact with your stationary phase. If there's no interaction, it's just going to elute and not have separation. So your compounds need to interact and you need to have differential interactions. So you need to have some selectivity so that you can separate. If 2 or 3 compounds are not having differential separation, they will co-elute and you won't achieve resolution. So you want to make sure that you have selectivity so that 2 compounds are separated rather than co-elution. And this part of resolution is mainly governed by your choice of stationary phase and your choice of mobile phase. So you can control that. You can control the selectivity based on, you know what your compounds are, then you select the specific stationary phase that these compounds will have differential interaction, differential partition coefficient, distribution coefficient, differential liking the column or the stationary phase. One thing we gave in the HPLC, one of your questions in the lab report, if you remember, I think Nigel would have gone over that with you, is when you have 2 peaks that are coming too close to each other, and you have acetonitrile is a very strong non-polar organic solvent. And if you want to make them interact differently, you might introduce methanol, which is a more polar organic solvent than acetonitrile. So then they won't move together as much. If it's too strong of an organic solvent, they want to move out quickly and not separate. If you use a less of a strong organic solvent like methanol, then you can achieve separation. So selectivity can be controlled by the type of the stationary phase, by the type of the mobile phase. And it is more impacting factor to the resolution than efficiency. So if you look at the equation here, so the resolution is impacted, we can call quadratically with the number of theoretical plates, but directly to the basically your selectivity. Okay, and as to remember alpha, we mentioned it before, it is the adjusted retention time taking into account the solvent front of one peak to the other. So peak 2 to peak 1, adjusted retention time, taking into consideration the solvent front. Okay. Then capacity is another important factor that impacts resolution. So what I'm trying to demonstrate here is this. So you start off with, at the beginning of the column or when the column is new, you start off with having really nice separation. So this is A, this is B, same as you see here, and you have very nice separation. Over time and with more use of the column, some of the functional groups will be washed off. So because you're using solvents, sometimes the solvents carry some functional groups off, so you lose capacity on the column, meaning ability of the compounds to bind on the column, you lose that. So what happens then, since you have less capacity, compounds, you start having shorter retention time because there's not enough functional groups to interact. They are retained on the stationary phase less. So you see that you have retention time going faster. So instead of A, let's say here 5 minutes, this is 10 minutes of retention time, then what you see is this might come out at 3 minutes, and this might come out at 4 minutes, and then you will have no separation. So they will spend less time on the column, and then you lose resolution. So basically, the capacity factor is retention times minus the solvent front over the solvent front. So it can get smaller with time because you lose functional groups. Any questions about efficiency, selectivity, capacity? So I would say that sometimes, depending on your objective, you might don't care that much about grade separation. You might want to care about separation, but not worry about collecting a fraction. So sometimes you go, like you learned in GC, there are the packed columns that are no longer used in GC, and then you have the capillary column where you have really very thin stationary phase. So with that, you have very short analytical run because your compounds don't have a lot of interaction time with the column because you have very thin stationary phase. So you have very short analytical time, and then you get really sharp peaks. In GC, you really have very sharp peaks compared to in LC. Because you use capillary columns with very, very small, thin surface of stationary phase where you don't have a lot of diffusion and you have more movement with the column and better separation. So sometimes you care for that. Sometimes you say, no, I need to collect my fractions. I need more to inject here. You can only inject a very tiny amount of sample. Otherwise, you get overload and you won't have good separation anyway. Okay, so that in mind, I want to move into after you form your get your separation the way you are best able to, then you need to analyze. There's the qualitative analysis and there's the quantitative analysis. So for qualitative analysis, that means you want to identify what the sample is or what the compound is. Is it present in my sample? Is it not present in my sample? And what is it? Is it glucose? Is it fructose? Is it sucrose? Or if it's a polyphenol, is it one of the isoflavones that you will be working on next week? Is it genistein? Is it diazine? What is it? So sometimes you look at the retention time and the standards, and you're just able to identify your compound based on retention time and based on the standards that you have. Sometimes you don't want to run standards. You just add if you want to know if this is glucose or fructose, you add a glucose to the sample, we say spiking, and then you see the glucose peak increase. And that's one way of identifying. We talked about photodiode array detector in HPLC. I'll talk about it more in terms of its principle later on, but this allows fingerprint. If you remember from the HPLC labs, you get a spectra. So you get so if you remember, you have your absorption and you have your lambda, which is the wavelength. So you have a range, let's say from 200 to 400 UV range, nanometer. That's the lambda. Lambda is in wavelength, in nanometer. And you have absorption, and then you can say, okay, I don't have any absorption at 200, and then I get some absorption here, and then nothing after 300, let's say. And then you go, okay, my lambda max is 249 nanometer. And then another compound will have a different. And we talked about that. And this has a 259 nanometer lambda max. Again, lambda max is the wavelength at which you have maximum absorption. So with photodiode array detector, you get a fingerprint for the compounds, and you can identify the compounds based on their absorption. So it kind of gives you a three-dimensional data. At every fraction of a second, you get a spectra. So that's very powerful. It has its limitation, but it's very powerful in detection. Sometimes you use multiple detectors in a row. Sometimes you want to look at multiple compounds. Some compounds absorb light, some compounds scatter light. So you go, okay, I'm going to use a UV detector followed by light scattering detector. And we're going to cover all of these detectors later on. Sometimes you have two compounds that have the same lambda max, but not necessarily the same absorption over a wide range of lambdas. So let's say, okay, let me illustrate. So sometimes you have here and here, sometimes you have the same lambda max, but you get some absorption at, let's say, 300 nanometer. And here you have very little absorption at 300 nanometer, but you have the same lambda max. In order to identify, you just take the ratio at two different wavelengths. Then you can differentiate the two. Sometimes, and we use this a lot in protein work, you use multiple chromatography separation in a row. So let's say we separate proteins based on size exclusion chromatography, then we separate them based on charge. Sometimes proteins have the same size, but they differ in charge. Sometimes they have the same charge, but they differ in size. So you need two-dimensional chromatography in order to separate them and identify them. And you learned mass spectrometry already, so it's a very powerful tool. It gives you a lot of information. First, if you're using soft ionization, you can get the molecular weight of the parent ion or the molecular ion. And if you do hard ionization, you get fragments, and the more fragments you can get, the more structural elucidation you have. And sometimes you do MS in tandem, one MS, second MS, third MS, where you take one ion, you break it further, you get more structural information. You take one of these ions, break it even more, you get more structural information and very powerful identification tool. Questions? All right. So we want to move into quantitative detection. And I'll later on show a different set of slides to explain external versus internal standard. And I know this has been a confusing topic over the years for students. But first of all, when we're doing quantitative analysis, you can take two measurements, peak height or peak area. That means area under the curve. Oftentimes it's peak area because it doesn't change when your resolution changes. So basically, if you start with a sharp peak, so if you start with a sharp peak and you have two sharp peaks, they would have a specific height. But then over time, over use of the column, you might lose some efficiency and the peak widens a little bit. But you're still getting resolution. You're fine, you don't need to change anything. But the height now is shorter. It's shorter than this. So taking the height is misleading in terms of quantity. If we take the area, this area will be equivalent to this area, this irrespective of the height. So it's always best to take the area because the height is dependent on the sensitivity of the detector, dependent on the efficiency of the column, whereas the area can be more directly related to the quantity. And we determine area, old school, you can use dimensions, or in the past they used strip chart. Nobody uses anymore. Now the program is smart enough, the software, to spit out the areas for you, and that's what you use in calculations. All right, let's spend a little bit of time talking about external standards versus internal standards. Can anybody tell me when external standards are used? Let's see what you know. When do we use external standards? Kevin, go for it.
In our GC lab, we use an external standard, just from like a company, or we use an external standard that would give us known fatty acids to give us a specific retention time.
Yes.
The peak area was comparable. So then we could take that, run on the same equipment that we ran our samples on, and then based on the unknowns of our samples, we could compare the retention times to the reference and
Identify.
them.
Very good. That's one use. Medora, did you have something else to add?
I was about to share more for like internal standards.
You're going to answer internal?
No, I was saying like, I was gonna share like about internal standards.
Okay, hold that thought. I want to know more about external standards. So Kevin gave a good example from GC that we use it for identification. If we run our standards and we look at the retention times, we can determine the compounds in our sample. That's what you did in GC. Go ahead, Stella.
For like the HPLC lab, we use an external standard to figure out the concentration based on the peak area.
Absolutely. In the HPLC, different than the GC, you not only use external standard at one concentration and ran it, you ran the external standard at different concentrations so you can get a standard curve to do quantification. So external standard is really important for identification sometimes and for quantification. If you don't have external standards, you're not able to do accurate quantification. So in the GC lab, we call it semi-quantitative because you got the relative areas, okay? And every fatty acid have a different response factor from the FID, from the flame ionization detector. So you were able only to get the relative area, but sometimes two compounds give you the same area, but they are present at different concentrations, and that's because they have different response from the detector. Okay, so in order to get a full quantitative data for the GC part that you did, we should have run a standard curve for every fatty acid. So we would have gotten the standard of every fatty acid and ran it under different concentrations and have a standard curve, so then you can quantify with accuracy your fatty acids. Okay, so external standards are really important for quantification. Okay, Medora, I'll go back to you in terms of internal standards.
I feel like internal standards are more so helpful when like you can't, like whatever you're analyzing is kind of like too complex or can interfere with like what analyte you're trying to detect. So you use an internal standard to kind of like how to know concentration, see like, for example, in concentration, like see how it may like change like as you increase interest. To compare that to how much it is.
Okay, I would say somewhat you are right. I would add to that the main importance of internal standards is basically you add it to your samples and it corrects for any losses you have during sample preparation. So especially when your sample preparation protocol is very long and it has multiple steps, like you did for the fatty acids. You had to subqualify, you had to methylate, you had to transfer, you had to add solvents and transfer and dry out. So many steps. So some of the fatty acids could be lost during sample prep. So if we use an internal standard at the beginning of the sample prep, whatever losses you have in your compounds of interest, you will have equivalent losses in your internal standards. So it corrects for sample preparation errors. So basically an internal standard, what are the characteristics of an internal standard? So if you want to choose an internal standard for your analysis, let's say you're doing fatty acids, what do you want your internal standard to be? You don't have to tell me the compound, but what would be a good internal standard? Medora?
Something that'll probably like dilute relatively within the same amount of time. So like, for example, the ability of fatty acids want to like have within that same carbon chain range.
Yes, that's one very important factor. You want it to elute within your run time. What else? Hey, Hallie, do you have your? All right, Stella.
Something that won't like overlap with what you are.
Yes, you don't want anything that co-elutes with your compounds of interest. So now you want them to elute separately, and you want it to be structurally similar to your compound of interest. So for example, you can get a C4 fatty acid and that has 4 carbons and use that as an internal standard, a synthetic C4 compound that is structurally similar to your compound. It will have similar response for your detector. So if I want to use an internal standard using a UV detection, I want to make sure that my internal standard is structurally similar and I can get absorption at the wavelength I'm screening. So it has to be structurally similar. So 3 things you want to remember: structurally similar, elutes separately, does not co-elute with any of your compounds, and is within your analysis run time. So 3 things to remember about characteristics of internal standard. All right, so now in this example, you are looking at the sugars in molasses. So the sugar in molasses, you have glucose, fructose, and sucrose. Lactose is not present in molasses. Lactose is present in dairy milk. So lactose can be your internal standard. It's a disaccharide. It's made up of glucose and galactose. So it will elute within your time frame. It's structurally different and it will not, so it's structurally similar, but it will not co-elute with any of your sugars of interest. So in this case, if I want to quantify, I want to use external standards. And if I want to correct for any sample preparation error, I will use internal standards. So internal standards does not give me quantification data, right?
I have a question basically on like, so you want it to be like non-reactive with stuff inside the column, right? So like.
No, you want it to react with the column, but you don't want
Oh,
it to
yeah,
be
not with any of the,
compound.
yeah. So like, just having something with similar structure, will that make it like automatically non-reactive with stuff?
If it has similar structure, you want to be very careful. You don't want it to be too similar so that it comes out with your compound. So you want it to be similar in structure so that it can be detected by your detection and also comes out within your retention time period. Does that answer your question?
Yeah.
Okay, good. All right. So I want to visually show you. I asked one of my TAs last year to kind of put some illustrations together. For internal standard definition, if you want to take pictures, you can, or else I will post this on Canvas. So internal standard, substance with known concentration. So you get a standard and you have a known concentration of that standard. And the criteria, the three criteria I mentioned, structurally similar, have different retention time, and elute within the analysis time. And the purpose to correct for any variability or sample loss during preparation. So to correct for any errors. So enhance your accuracy, basically. The external standard is whatever your compounds that you're looking at, you need to have an external standard for. Glucose in your sample, in molasses, you need to get glucose standard. Sucrose, sucrose standard, and so on. And it's not added to the sample, it's just used like we did in the caffeine lab, used to construct your standard curve. Okay, and it contains this, so that's the criteria. It is the same compound that you are analyzing. And the purpose is to get the calibration curve and to quantify. Without external standard, again, I stress, cannot quantify. You get a relative abundance maybe, but not necessarily concentration. So your lab task in this example, you have molasses sample and you want to determine the amount of sucrose, glucose, and fructose. Use the internal standard lactose and the external standards that you have for glucose, fructose, and sucrose to generate a standard curve. So this is what you would want to do. So lactose is a disaccharide of glucose and galactose. You have the sucrose, which is a disaccharide of glucose and fructose, and you have glucose monomer and fructose monomer in your molasses. So you have to have those external standards, and you have the lactose as your internal standard. So that red dot is an indication of your internal standard. So you add the same amount of your lactose, same concentration, same volume, to all of your standards. So you prepare standards at different concentration and you add the same amount of lactose to all of them. And then you add the same amount of lactose to your sample as well. Whatever you added to your standard, you add to your sample and you start your analysis. So now when you run your standards, glucose has lactose in it, in your standard. Fructose has a known lactose, and sucrose has a known lactose in it. Then you construct your standard curve. How do you construct your standard curve? You see each peak here? You take the peak area of glucose and you divide it, you take the ratio, you divide it by the area of the lactose. So peak area ratio, area of external standard over area of internal standard. So your y-axis, instead of it being only area of your external standard, now you are correcting for the area of the internal standard. That will be your y-axis. Your x-axis is the concentration of the different sugars, okay? So you will have 3 standard curves, not 1, 3, because you have 3 standards. And then you will have 3 equations of the line, 1 for fructose, 1 for sucrose, and 1 for glucose. Any questions here, or is this clear? Yes, Captain.
Would you always use this kind of setup for an internal standard,
Yes,
like in tandem with an external standard, you would never use just the internal standard?
you can use an internal standard alone, and then you can only get the relative abundance. So you won't be able to get, like out of like 100% of your total area, you'll get the relative abundance of each compound by correcting with the internal standard. So it will be kind of a semi-quantitative. But if you want to get a concentration, you need external standards. So now, any other questions here? Okay, then in your sample now, you ran your standards, you have your 3 equations of the line, then you run your sample, the molasses, it also has the same amount of lactose in it. So again, in order to get the concentration of, let's say, glucose, you want to take the area of glucose by the area of your lactose. You get that ratio, and that's your y. And then you have the slope, you have the intercept, and then you calculate the x. So always remember, you take the ratio of your compound to the ratio of the area of your compound to the area of the internal standard. Yeah? Okay. Any questions there? All right, so that's it for the chromatography. I have a little bit more of time, 12 minutes or so. I will start the HPLC refresher, because you already did the lab. Let me get the lecture here up. Thinking. All right. First of all, I want to see hands up and honest hands up for who watched the video, YouTube video for the HPLC. All right, about half of you watched it, the YouTube video about the HPLC. Okay, I encourage those that did not watch it to please watch it so that I don't use class time, especially if half of you have seen it already. So HPLC, it stands for High Performance Liquid Chromatography. It originally was high pressure liquid chromatography because when we started using these packed columns that you saw in the lab, they're packed under pressure. And they used to generate really high back pressure, and the pressure of the system would be really high. But over the time, they got better at packing these columns. So, and that you had better performance. So they replaced the pressure by performance. So now it's high performance liquid chromatography. And a former TA of mine, about, I don't know, 10 years ago, used your caffeine samples to draw an HPLC. So I thought that was cute and I kept it. All right, so what are differences between a high performance liquid chromatography and the traditional low pressure liquid chromatography? When I say low pressure liquid chromatography, these are the big columns that we pack ourselves following manufacturer instructions and usually are used for fractionation and collection of fractions. So you don't get great resolution with those columns. So with high performance liquid chromatography, you get speed. So your analysis time is much shorter. We run, let's say, hydrophobic interaction chromatography on large low pressure columns in our lab, and then the analysis time is about 90 minutes. And you have the pre-equilibration and post-equilibration. One run can take 2 to 3 hours to perform. So that is not efficient use of time, but you don't have a choice when you need to collect large amount of sample for further analysis. So you get speed, you get enhanced resolution, because now you have really well packed column where you don't have a lot of spaces in between the particles, and you don't have large particles, so that you will have better efficiency. If you remember, you need to remember the relationship of the particle size, the pore size, and the packing. So I'm going to illustrate a little bit just to remind you. I know I covered this, but I want to make sure that you guys know what I'm talking about. So then, first of all, you have particle size. And then this is particle size, okay? And then you have pores within the particles, pores. And then you have different pore sizes. And then you have space in between. So either very well packed or not very well packed, where you have a lot of space. So in high performance liquid chromatography, you have small particle size, very well packed. You have very little space in between. So you don't have a lot of diffusion within the column. And then also you have very small pore sizes. So you also don't get the sample lost within the stationary phase. So you have the bands moving down your column will remain sharp, giving you really sharp peaks. However, in this case, when you have large particle size, large pores, space in between, you really get this kind of chromatogram. But then you would go, okay, I'm going to collect from here to here. I know this is a pure compound, and then I'm going to collect from here to here, and from here to here, and from here to here. And then you say, okay, these are the fractions I'm collecting, and I'm going to do further analysis on them. So you don't have the luxury to have these great resolution. Another thing about packed columns is that you can reuse them for a long time. If you take good care of them, you do the conditioning of the column, we call it, based on manufacturer recommendation. After you run, let's say 100 injections, you just wash the column, clean it, regenerate it, and then it will last you a long time. Depending on what you're injecting and what is your mobile phase, a column can last for 1,000 injection to 3,000 injection. Whereas the low pressure chromatography columns, you have to repack again and again because you lose some of the particles because they are loosely packed compared to the high performance liquid chromatography columns. Easy sample recovery because you have good separation. If you want to collect, you can. Sometimes we collect from high performance liquid chromatography, but it would be a very small amount, very dilute, and we can take it for MS analysis, for example, because they don't need high concentration of sample. Okay. The compartments, you're already familiar now because you've done the lab. We have the reservoir where we have our solvent, and we have a pump. The example you saw in the lab is 2 pumps, because most of the time we have binary system. You have 2 solvents and you do a gradient elution. And the pump will pump the mobile phase to the injector. And at the injector, you have either a manual injector or an auto injector where the sample is injected and the mobile phase carries the sample to the column. And now your constituents are interacting with the stationary phase in the column and separating based on their specificity and selectivity of your column and your mobile phase. And then hopefully one by one will reach your detector. And we have a number of detectors that I will be covering for HPLC. And after they get to the detector, if it's whatever is the signal, it's an absorption or light scattering or refractive index, whatever is the signal is transformed into an electrical signal that the software can convert to an area under the curve for you. And sometimes after the detector, if we want to collect each peak, we have a fraction collector that would be timed based on our retention times to collect samples at known times. So this is kind of the general setup. Yes.
Is there any benefit or like, to, like, could you rerun your fractions through the same like HPLC? Like if you have things that are co-eluding kind of thing, like would running the co-eluding fraction, would running that through the same column, would that separate them, give them more time, or no, they would still come out the same?
Good, very good question. Did you all hear Kevin's question? His question was, if we collect the sample and we have two compounds co-eluting, does it help to run it again through the system, the same system? Will they separate? So yes and no. First of all, the longer the column, the better separation you get. So if you think that I can run it on two columns consecutive, I might get better separation and separate them because you have longer time to get this nice separation. But another thing that you would do is you would just separate them on a different type of media. So then that'd be 2D. That's the example we gave when you have size exclusion followed by ion exchange. So we collect this fraction and we actually rerun it on a different matrix and get separation. So that's exactly a very good example for when we use fraction collection, is take a sample from size exclusion and then inject it on an ion exchange column and get better separation and purification. Very good question. So we have a pump that allows us with the HPLC to have constant pressure or constant volume. So we can adjust the pump to have a specific rate. So let's say 1 ml per minute, 1 ml per minute of pumping, 1.2 ml, 0.5 ml. So you can regulate and the pump will pump the rate that the software is giving it. In HPLC, we have a system with low pressure mixing and a system with high pressure mixing. What does it mean? So you have your reservoirs. So you have your 1 bottle, 2 bottle there. You can have a mixer here. And then it goes to the pump. High pressure pump. So we call this low pressure mixing. So it's mixing before it gets to the pump. And then on the other side, we can have this and this go to different pumps. Pump 1, like pump A, and then another one going to pump B, which you saw in the lab. And then when they come out of here, you have a mixer. We call this high pressure because they are pumped under pressure. And then you have channels in there that allows the mobile phase to mix really, really well. And out of here, you get a very homogeneous mobile phase. So I prefer the high pressure mixing in my lab. I don't have low pressure mixing because with high pressure mixing and very homogeneous mobile phase, you get really nice baseline. sometimes if you don't have, I mean, this is more expensive. You can use low pressure mixing, that's fine, but maybe your baseline is a little bit not straight, you know, because the mobile phase is not completely mixed very well under pressure. So you might not really have a nice smooth baseline. So depending on your system in the lab and your purpose of the experiment, you might go either way. Okay, I think we reached the end for today. I'll see you on Monday. Thank you.